In this lesson, I'm going to teach you a general technique that you can use to graph any exponential function. In order to graph exponentials, you have to remember first that they have only one unknown parameter. The only thing we really get to pick is the value of this number, a. By changing the number a, you end up with a completely different shape for your exponential. But despite the fact that exponentials only need one parameter, we actually draw 2 points because that makes it a lot easier to actually draw the graph. Now, if you look carefully at this function, if you were to sub in x equals 0, well, anything to the power of 0 is always going to be 1. So f of 0 always has to be 1, no matter what a you choose. There's actually one more really easy point that we can use as well. If we allowed x to equal the number 1, then a to the power of 1 would just end up being the same thing as a. So that immediately tells us that f of 1 has to be equal to a. So I've drawn an xy axis here, where I've labeled the x-axis as capital X and the y-axis as capital Y. The reason I've done that will become very clear very soon. But no matter what our graph is going to look like, it's going to have to go through the point 0, 1, and it's always going to go through the point 1a, no matter what the value of a is. Now, since this point over here represents a y value of 1, in this picture I've actually assumed that the value of a we've chosen is larger than 1. And that's very clear because the y value is bigger than this number 1. To help us construct the rest of this graph, let's continue operating under the assumption that a is going to stay larger than 1, at least for now. So to help us do this, how about I bring over a scrap piece of paper and we'll look at what the rest of the graph looks like for a particular choice of a. So instead of thinking about a to the power of x, how about we just try graphing 2 to the power of x? Because that's going to be pretty straightforward. We know that when x is equal to 0, 2 to the power of 0 is still going to be 1. And when a is equal to 1, then 2 to the power of 1 is just going to be 2. So we know that it goes through 0, 1 and 1, 2. So just as we did before, I marked on the entire graph and now I graphed on 0, 1 and 1, 2. But we want the rest of the points. But now that we have an actual example, it's pretty easy to find them. For example, if x was equal to 2, let's think about what would happen to f of x. Well, that's going to be 2 to the power of 2, and that's the same thing as 4. So we would expect the graph to go through 2, 4. Similarly, if we tried x equals 3, then we'd end up going through 2 to the power of 3, and that's going to be 8. So we go through the point 3, 8 as well. Well, without continuing this for too much longer, how about we just add on one more point? Let's suppose for a moment that x was actually equal to negative 1. Well, then we'd have 2 to the power of negative 1, and that would be the same thing as 1/2. So we know that the graph also goes through negative 1, 1/2. And in fact, if you made the value of x smaller, what would end up happening is you'd end up dividing by 2 more times. And that's just going to keep driving the value closer and closer to 0. So that means the graph is just going to get closer and closer to 0 as x gets more and more negative. And at this point, it's just a matter of playing connect the dots. If we were to just connect the dots, we would end up with a graph of the exponential function. And you can see that it looks a little bit like this. So this is the shape of an exponential, but we didn't really need to find all of these points. As long as you had these 2 points over here, you'd know that the exponential follows this approximate shape. And therefore we can also apply this to this graph on the left as well. So now that we know how to graph exponentials whenever a is greater than 1, we should also think about how to graph them when a is actually between 0 and 1. Now before I show you this, I just want to make a quick side note. We can graph a greater than 1, and we can graph a being between 0 and 1, but we never graph a as a negative number. The reason we never allow a to be a negative number is because we may end up choosing a to be something like -1, which is totally fair. If you then raised it to the power of x, choosing x to be 1/2, then that's the same thing as the square root of -1. You may or may not know about the square root of -1, but it's not very well defined, so this is actually impossible to graph. And for this reason, we always choose a to be a positive number. We just break it up into the 2 cases where a is bigger than 1 and a is less than 1. But to be totally honest with you, these two cases aren't really all that different. So to prove that to you, how about I actually graph something like 1/2 to the power of x? So to graph this, we're going to look for the same 2 points that we did over here. In the situation where x is equal to 0, we're going to get the same thing. Anything to the power of 0 is always 1. Similarly, when x equals 1, then 1/2 to the power of 1 is still just 1/2. Now the rules don't change in this case. Since we have the same 2 points over here, we're just going to draw the graph that goes between them. But since this number is smaller, the graph's actually going to end up looking like this. Now, if you'd like to verify this yourself, I urge you to actually test a few more points to make sure that this actually does work, just like we did for the blue graph. But I'd like to give you another way to actually visualize this that's going to be relevant to the next technique I'm about to show you. So I just want to rewrite this 1/2 as 2 to the power of -1. Now at this stage, we can just go ahead and use the index laws directly. So we can rewrite this as 2 to the power of -x. Now this is actually pretty interesting, because 2 to the power of -x can be constructed from 2 to the power of x by flipping 2 to the power of x across the y-axis, because after all, replacing x for -x just flips the y-axis. And this definitely looks true. I mean, this is the graph of 2 to the power of x, and this is the graph of 2 to the power of -x, which is the same thing as 1/2 to the power of x, and they do look like they've been flipped around the y-axis. So therefore, to convert the graph of a to the power of x to the graph of a to the power of -x, all you need to do is to flip this across the y-axis. So the main point you need to know here, whether or not the value of a is bigger than 1 or less than 1, you always need to find the value at 0 and the value at 1. Once you know those 2 points, you can easily just draw the graph very, very easily. Now, because the a you're starting with always has to be a positive number, no matter what power you raise it to, you're always going to end up with a positive number. So the y value always needs to be a positive number as well. So the easiest way to graph this is to just put down 2 dots and then play join the dots with the exponential graph, just remembering the shape of the graph. But we can actually perform other transformations as well, other than the simple flip transformation. So how about I show you how to actually transform this graph to other places as well. Now, whilst this is the basic shape of an exponential graph, we would also consider any transformed version of this an exponential graph as well. For example, you may take this graph and decide to lift it up by 2 units, or you might decide to flip it around the x-axis so it looks like this, or maybe you then flip around the x and then flip around the y. Or you could even combine more than one transformation. You might start with this graph, lift it by 2, then move it to the left by 3, and also flip it around the y-axis so it looks like this. So we also need to figure out how to actually draw graphs in that form. Now, this is the point where those capital letters come in. We're going to refer to this axis as the capital X, capital Y axis. In a sense, this is the original exponential, y equals a to the power of x, where y and x are capital letters. We are going to replace this graph for this graph over here, where y is equal to ka plus b x minus c plus h. Now, this can look a little bit intimidating when you first see it, but I just want you to realize that each of these new letters that I've added just allow for a different kind of transformation. For example, this value of k here relates to how much we stretch in the up and down direction. So we could take this graph and then squish it down to look like this, or we can even flip it. Then similarly, this b over here does something very similar for the x-axis. For example, we could squish it so that the graph is thinner, or we could flip the axis in the x direction. And that's what this b allows us to do. The c is going to let us move the graph left and right, so for example we can move it like this. And the h is actually going to let us move the graph up and down, like this. So because there are 4 possible transformations, I've actually added on 4 parameters, and each of these parameters controls a different transformation. So the whole idea here is to think about where this whole graph is going to move under the action of this transformation. Now, in order to graph the transformed version of this function, we need to think about where 2 different points on the original x and y axis are actually going to map to on the new axis. So just to help us see exactly what's going on, I've drawn a point at the origin, which is just the point 0, 0. And we're also going to look at this point 1a. Under the action of the transformation, these 2 points are going to end up mapping somewhere in this new axis. The cool thing about a simple transformation like this is that if we know where this point went and where this point went, we technically know where every single point went. To think about this, imagine this was made of a sheet of rubber, and you put your finger here and another finger here. You then moved your first finger here and your second finger here. Well, all the space in between is also going to move to here as well. And if this is true, if the exponential looked like this before, now it's just going to look like this. And it's never going to pass this line down here. So this line becomes your asymptote. Now, if this is going to be the shape of our graph, then the only question left to answer is where do these points actually go? And that's a question we can answer really easily. So to figure out where our points actually went, we're going to need to somehow rewrite capital X and capital Y in terms of little x and little y. Now to do that, let's just rearrange this formula so it looks a little bit like the one on the left. So for starters, we don't have any extra constants on the right hand side. So what I'm going to do is I'm going to move this h to the left hand side. And when I do that, I end up with y minus h. After this, we also notice that we don't have anything in front of the a. So I'm also going to divide both sides by k. And now, if we assume that these two formulas actually represent the same graph, which is the graph of this exponential, then we can immediately state that capital X must be the same thing as b times x minus c, and capital Y must be the same thing as y minus h on k. Now initially, these two formulas can seem a little bit confusing, but let me actually show you how to use them with an example, and you'll see that it's actually not confusing at all. So for example, let's imagine we wanted to graph y equals 3 times e all to the power of 2 minus 3x, all plus 4. Well, that looks pretty similar to this form over here, but it's not quite the same. To do this, you just have to realize that this e here is going to be what we're using for the value of a. Remember, e is Euler's number, and it's equal to approximately 2.71. I did a whole video on Euler's number if you'd like to learn a little bit more about it and where it comes from. But either way, our first goal is going to be to rewrite this all as y equals a to the power of x, but instead of a, we're using e. So just like we did over here, I'm going to start by moving the 4 over to the left and then dividing by 3. Now at this stage, we can see that this y minus 4 all on 3 is the same thing as capital Y, and 2 minus 3x is the same thing as capital X. So we should start with the graph of capital Y equals e to the power of capital X. So let's do that first. After this, we choose 2 points to track around. So I'm going to choose the origin again, and I'm also going to choose 1e. And because we know their coordinates in the capital X and capital Y axis, we can use these formulas to find out the new coordinates in the little x and little y axis. So let's start by looking at the x coordinate of the origin. When capital X equals 0, we can just replace this capital X for 0, and that'll help us find little x. Now we can just move this 3x to the left-hand side, and then we can just divide both sides by the number 3. Now under this transformation, when capital X is equal to 0, then little x must be the same thing as 2/3. We can also do the same thing for this transformation over here. So let's try to figure out what happens when capital Y also equals 0. Now before I do this, I hope you realized when we were doing this that it's probably a good idea to make little x the subject of this equation and little y the subject of this equation. Because if little x was the subject, then we could just sub into capital X and capital Y directly. So let's go ahead and make little y the subject of this equation. Making little y the subject is reasonably straightforward. All I need to do is I need to take this 3 and move it to the other side, and then I need to add 4 to both sides. So we can see that little y is equal to 3 times capital Y plus 4. Now, because this is going to make our life a fair bit easier, I'm also going to do the same thing to this equation as well. I'm going to start by pushing the 2 to the left-hand side, and then I'm going to divide both sides by this negative 3. So little x must be equal to capital X minus 2 all over minus 3. Now at this point, finding the values of little x and little y are going to be really easy. For example, when capital X equals 0, we could just put a 0 over here, and we could find that little x is minus 2 on minus 3, or 2/3. So similarly, when capital Y equals 0, we could just put a 0 in here, and then little y would just be 4. We also want to know where little x goes when capital X equals 1, as you can see here. So if we plugged in x equal to 1, then 1 minus 2 is minus 1, and minus 1 on minus 3 is just the same thing as 1/3. And finally, we also want to know where little y goes when capital Y is equal to the number e. So if we plug in capital Y for e, that would just be 3 times e plus 4. And that can't really be simplified because e is a real number. Now at this point, we just go ahead and mark all of this information directly on a graph. So when x equals 0 and y equals 0, we're looking at this point over here, and that maps to 2/3 and 4. So that's going to be this point over here. And then, when capital X equals 1 and y equals e, we have the point 1/3 and 3e plus 4, and that's going to be this point right here. Now, when you compare these two boxes here, you can see that our transformation has actually moved the blue point to the left, as you can see here. Now, because the box has actually flipped in the x direction, this means that the graph must also flip in the x direction as well. So our graph is going to look something like I've drawn there. It's also quite common to graph in the y-intercept as well, and we can do that easily by just subbing in little x equals 0 into this equation over here. So if little x does equal 0, then this will just go away, and you're left with 3e squared plus 4. Now, constructing an accurate graph like this one is actually a fair bit of work, and obviously there are graphing packages available all over the internet that you can use. But despite the fact that graphing software can do this for you, being able to draw it by hand actually allows you to understand quite a bit about what these numbers are doing. For example, since this was a negative number here, we could see that there was a flip along the x-axis. And this 3 in front of the y just tells us that the graph would have been stretched upwards. So depending on what problem you're trying to solve, you can come up with a reasonably quick and approximate graph of this function over here, if you need it. Now, one of the interesting things about this graph is that this 4 has just raised the function by 4, so the new asymptote is now going to be y equals 4. But either way, in general, we need to just rearrange these two formulas in order to make little y and little x the subject, just as we did over here. So for this first formula, I'm just going to multiply the k over, and I'm going to bring the h over to the other side, making it positive. And that tells us that little y must be the same thing as k times capital Y plus h. Similarly, on the right hand side, I'm going to need to divide by b first, and then I'm going to need to add c to both sides. And then, just like we did in the example over here, we can also think about where x equals 0 and x equals 1 map to, with this formula over here. So if capital X equals 0, then we just rub this whole term out, and we just get x equals c. And then, if capital X equals 1, then we just get 1 on b plus c. And then given this information, we can actually graph this on the axis that's hidden by the piece of paper. So I think it's a good time to get rid of the piece of paper for now. So as we saw, when capital X was equal to 0, then little x is actually going to be equal to c. So this point is going to be c. Also, when capital X equals 1, which is this point, then little x is going to be 1 over b plus c. So that's going to be this point over here. We also want to do the same thing for the y coordinates as well. So looking at this point, when capital Y equals 0, we just cross this out, and we just get little y equals h. And then similarly, for this point, capital Y equals a, and if that's the case, then little y is going to be k times a plus h. And therefore, this is actually going to be the graph of our transform function over here. You can see that the point 0, 0 just goes to the coordinate ch, and those numbers just appear directly in our function. And then from there, the letters k and b dictate how much we're going to stretch in the x direction and in the y direction. And that just about summarizes how we can turn this box into this box over here, and also how we can graph any exponential we like by using a transformation. So therefore, I'd just like to summarize this lesson. In this lesson, we talked about how we can graph exponential functions. We started off with the graph of the basic exponential function, and then we talked about how we could graph a transformed version of it. We said that for a simple exponential function, like a to the power of x, the numbers will just get bigger and bigger as x gets larger and larger. But that assumes that the value of a is actually larger than 1. In the situation where the value is between 0 and 1, the value actually ends up decreasing very, very quickly. Therefore, we said that whenever a is greater than 1, you'd expect this to be the shape of your exponential. And whenever a is less than 1, then this is going to be the shape of your exponential. All you need to do to graph your exponential is to look at this point over here, which is 0, 1, and this point over here, which is 1a. We said that you could always choose a to be any positive number, but you can't choose a to be a negative number, because if you did, we wouldn't know what to do when x was actually a fractional power. After this, we tried to figure out how to transform these 2 points to give us a transformed version of the exponential. So we wrote the exponential as capital Y equals a to the power of x, and then said we could transform it into little y equals ka to the power of bx minus c, all plus h. After rearranging these two formulas a little bit, we were able to figure out where the pink point maps and also where the yellow point maps. And then from there, we were able to turn this graph into this graph over here. And this is actually a good general method to actually graph any exponential you like. Now, I also mentioned that we could graph an exponential like this one over here with a piece of graphing software. But being able to graph it yourself allows you to understand what all these different parameters actually do to the shape of the graph. But at this point, that just about completes everything I wanted to say about graphing exponentials. So no matter what exponential I give you, I think it should be possible to graph it with the techniques that I've shown in this video. Thanks for watching another Trina video. If you want to say thanks, you got to show your friends. Or maybe you should just visit us at trina.org, where you can track your progress and have access to questions and heaps of other awesome stuff. Or maybe you should just like and subscribe. That works too. But either way, I'll see you next time.